All right. So a couple of things. Who had trouble in the end, doing stuff on VoiceThread? Few people. I expected that. Okay. So what I learned through this first experience is it is a huge pain in the rear end, right? Yeah. I think that I think I've figured out a couple of the issues. So I want to just spend a few minutes talking about that real quick, and then show you a couple of things that I put out that may help. We don't do another one of these VoiceThread assignments until September 7th is the next time. So we've got about a couple of weeks to play around with it beforehand. But those of you that were able to do it, thank you. I appreciate it. Those of you that weren't, don't worry. You still get an opportunity for your 2 points today too. So the first thing I want to point out is over here under Tools, under the Tutorials, I've put a couple of things in here that I added either last night or this morning. So the first one is just this general help. It seems like there's two common issues, or ones that I think maybe we're overlooking. One, I put in the announcements, if you have your settings in your browser to not allow third-party cookies, it doesn't work. You have to change those settings. So the top link there is to kind of walk you through this process. The second one, and Lord knows why this is even an issue. I'm going to go to one of these voice threads real quick. And let's say I click on the mini lecture. Now people are going to get here and they're going to hit launch. That's apparently a no-no. Apparently you need to let this go automatically.
So it was not letting me
Okay.
go in.
I will, so for those of you who haven't tried yet, do try to see if you can do it. Otherwise, I will see if there's another way. Okay, I'll work on my end to figure it out as well. All right. Now with all of that said, now I'm going to force you to get up for like 5 minutes and move around real quick. So, I think in this class we have groups 11 through 17. So here's what we're going to do. Group 11, you get to stand right up here. And then we'll do like 12, 13, 14, 15, 16, and 17. All I want you to do is, I know not everybody got the chance to kind of talk online or anything, so I just want you to have the opportunity, if you don't know each other yet, to introduce yourselves to each other, and then to discuss the question as well. What is it that a molecule is hydrophilic or hydrophobic? Okay? Take about 3 minutes. All right. So let's just start off with just a broad conversation. Hydrophilic means what? Water-loving. Hydrophobic? Water-loving. Okay. What do we actually mean by that at the molecular level? So if something is hydrophilic, what are some characteristics of that molecule? How? How does it bond? And what I'm really trying to get at here is, what kind of bond are you talking about? So are we talking ionic, covalent, hydrogen? It is a hydrogen bond, is the one that we're talking about here. And so we'll cover that in a minute. What else? What gives those hydrophilic molecules the ability to form hydrogen bonds? For hydrophilic?
Are we doing hydrophobic or philic?
Philic right now. Then they're polar. Okay. What do we mean by that? What do we mean by the fact that bonds are polar? Yes. Good. And I like the fact that you're saying slightly instead of one end is positive and one is negative, because it really comes down to the term that we use oftentimes is partial positive and partial negative charges as a way to define these. Okay? So the bonds are still shared, or sorry, the electrons are still shared in a bond between two atoms, but the sharing is unequal in some way. So prime examples, and we'll talk about a couple of these. We'll take a look at, well, it's Friday, so I'll draw it out and then you can guess. It's like the worst game of Pictionary, right? What is it?
A pig.
No. What molecule? What molecule? Huh? No, I didn't hear what you said. Oh, it is. It is. Happy Friday. All right. Ethanol. Okay? So here's ethanol. I know, you guys are perfect. So where are there polar bonds in this molecule? And that question really depends on what we call electronegativity. So electronegativity is essentially essentially an atom's ability to hold on to electrons or to pull electrons towards it. Out of the atoms that we talk about most frequently and that we'll worry about most frequently throughout the semester, carbon, hydrogen, oxygen, and nitrogen. Oxygen is the most electronegative of all of them. I'm going to write down the values for these real quick. I am never going to expect you to memorize these, but what I expect you to do is to be able to use these numbers in some way. And let me explain that. So hydrogen's 2.1, carbon's 2.5, nitrogen is 3.0, and oxygen is 3.5. So what these values actually mean, as that number increases, it means that that atom will be able to hold on to electrons more tightly. So, for example, in an oxygen-hydrogen bond, oxygen holds on to the electrons more tightly than does the hydrogen. Since the oxygen is pulling those electrons towards it, we give it a partial negative charge. That's not an S, it's the Greek symbol delta. And then the hydrogen, since those electrons are being pulled away from it, it's as if it's being unshielded from those electrons. So the protons at the nucleus then provide this partial positive charge. Okay. Mathematically, the electronegativity differences that are equal to or greater than 0.5, those types of those differences are considered to lead to covalent polar bonds. So in other words, difference between the electronegativities of oxygen and hydrogen is, anybody wants to do mental math right now? 3.5 minus 2.1.
Oh, 0.9.
3.5 minus 2.1?
Oh, sorry.
No, that's okay. You did nitrogen and hydrogen. I'll take that one too, though. Let's do nitrogen and hydrogen.
Okay.
All right? 0.9 is the difference. Is 0.9 greater than 0.5? The answer should be yes. Okay? And so in that case, we consider a nitrogen-hydrogen bond based on those electronegativity differences to be a polar bond. Oxygen-hydrogen, difference is 1.4, polar as well. What bonds are not polar? So of these four atoms up here, which ones would lead to covalent but non-polar bonds being formed?
Hydrogen and carbon.
Hydrogen and carbon definitely is one example. Okay, and hydrocarbons, molecules that are made out of solely hydrogen and carbon, are what? Hydrophilic or hydrophobic? So oils. Hydrophobic, right? And so what I'm trying to point out here is that polarity, those partial positive and partial negative charges, that contributes to the hydrophilic and hydrophobic properties of these molecules. Oil, does it dissolve in water? Does it mix with water? No. There's another property that's associated. Hydrophilic, polar covalent bonds, can be dissolved in water, forms hydrogen bonds with water, and then the opposite for hydrophobic. Nonpolar bonds, can't hydrogen bond with water. What am I missing? Can't be dissolved in water. Okay, so those are the terms that you can start to associate with each other. Are there other ones that are nonpolar covalent bonds that might form? What about oxygen-oxygen? So O2. Would that bond be polar or nonpolar? be nonpolar, right? 3.5 minus 3.5 will always be 0. So we consider those bonds between two carbons or between two nitrogens to also be nonpolar bonds. That's why gases like oxygen, that does not dissolve in water very well. All right. Any questions on this principle? Okay. Let's take a look at solubility real quick. I'm just going to move ahead a couple of slides here and just take a look at this. So coming to back to that idea of hydrogen bonding, these hydrogen bonds are created through partial positive charges interacting with partial negative. Okay? The way that we typically model these is with some sort of dashed line to indicate this interaction. And I like to think of these as electrostatic interactions. In other words, it's kind of similar to how a positive and negative end of a molecule would attract to each other. We can say that these hydrogen bonds are either intermolecular or intramolecular. And what we mean by that is they can occur between two molecules, as in this example up here, or they actually can occur within a molecule as well. So for example, proteins are made up of many, many amino acids, as we'll talk about on Monday. And the hydrogen bonds that occur within amino acids contributes to its secondary and tertiary, so its globular folded structure. So that hydrogen bonding can play a really important role there. We can also get hydrogen bonding or interactions between molecules that are fully negative charged or fully positive charged as well. So in this case, hydrogen with a chloride ion allows for example, sodium chloride or table salt to be dissolved in water. Talking about dissolving, let's say I have a cube of sugar. If I take a cube of sugar, put it into a glass of water, what's going to happen if I stir that up? It's going to dissolve, right? When we say that that cube of sugar dissolves, what do we, again, at a molecular level, what do we actually mean? What's happening there? What's breaking? What bonds? Between what? Hydrogen bonds between what? And I'm glad you said bonds are breaking. The reason why is this is exactly a point I wanted to make sure to make. So thank you. Sometimes, and this is where we need to be a little careful with our language. So something we're going to be practicing throughout the semester is making sure that what we're saying is what we intend to say. All right? When we say that bonds are breaking between, for example, one sucrose molecule and another in table sugar, we don't mean that covalent bonds are breaking. At the end of the day, you still have sucrose, but it's been broken into, or those individual molecules of sucrose have been separated from each other, right? So in essence, what's happening, erase this real quick, we've got a molecule of glucose, and don't feel like you have to write this. You could just write glucose if you want to right now. Each of these molecules of glucose, or if in the case of table or just regular sucrose, table sugar, what we find are hydrogen bonds forming between, well, what would be forming hydrogen bonds here? So what parts of that glucose molecule would be forming hydrogen bonds with water? Yeah, the oxygens. So the OH groups, this is an oxygen bound to, and you'll see this in the next mini lecture, these are carbons here at these junctures. So we've got an oxygen-carbon bond that's polar, we've got an oxygen-hydrogen bond that's polar. So those provide opportunities for hydrogen bonding to occur with water. Who has seen the Harry Potter movies? The first one at least. And I'm going to assume most hands are going to raise. Maybe not. If not, I don't know what the heck's wrong, but okay. Or if you've read the books, Harry Potter has a cloak, right? An invisibility cloak. All right, and I use this as an example every year. The invisibility cloak, in some ways, is like what happens when a molecule is dissolved by water. So imagine Harry Potter as a glucose molecule. He puts on the invisibility cloak, and you now can't see that molecule of glucose anymore. Water forms what we call a hydration shell around molecules that it dissolves. In other words, it basically kind of hides the image of whatever it's dissolving, which is why, for example, when you put sodium chloride in water, when you put sugar in water, you no longer see the sugar. It's because the light is kind of bouncing around it with the water molecules that are protecting that particular molecule. Okay? There are exceptions to this, though. Will all hydrophilic molecules be dissolved in water? Who says yes? You can raise your hands if you would like to. No? One is bold enough. I don't know. What the hell is he talking about? Yep, there we go. All right. Did anybody take a shower last night or today at some point? I did too. Okay. What did you use to dry off after that shower? Okay, thank you. Perfect.
A beach towel with a turtle on it.
Even better. All right. That beach towel made with a turtle on it. What's it made out of?
Fabric.
What kind of fabric?
Cotton.
The fabric of our lives, right? Okay. So made out of cotton. What is cotton at the molecular level? Is it a carbohydrate, protein? It's basically a bunch of glucose molecules attached to each other through covalent bonds. Okay? So long strands of glucose lead to the formation of starches, cottons, etc. When you dried off, did your towel dissolve?
No.
Thank the Lord, no, right? Okay, so it didn't dissolve. Why not? It's hydrophilic. It can form hydrogen bonds with water. It's polar. Why didn't it dissolve? There's really two things that dictate solubility, or there are a couple of things that dictate solubility. One is how much, concentration. So go back to the sugar model. If you keep just adding sugar to water, at some point that sugar can no longer be dissolved. You've reached a saturation point. With something like a towel, the polysaccharides, those long strands of glucose, are too big. They're too large to actually create a hydration shell around. And so that's why something like a towel isn't dissolved in water. So size and concentration play a big role in determining can something be dissolved or not. Any questions about towels? Anything like that? All right. Let's move on. Here's what we'll do. In pairs on your own, you can decide how you want to spend the next couple of minutes. But what I want you to do is, let's go ahead and discuss pH, acid, bases, hydrogen ion concentration, and buffers if you want to as well. What's the relationship? So in other words, how does hydrogen ion concentration relate to pH, or to acids or bases? Okay. Take a couple of minutes, either jot down some notes, talk it out with somebody else. Go. How about the OH, the hydroxide, OH negative concentration? As pH decreases, so as it goes from 7 towards 1, what happens to the OH concentration? Yeah, it's going to decrease as well. So it's going to go from 1 times 10 to the negative 7th to, what would that be, 1 times 10 to the negative 14th or something like that at a pH of 1. Okay. let's see, what else do we need to cover here? The reason why I take the time to cover this real quickly is because when it comes to pH, I really enjoy this table for a couple of reasons, but one of them is pH is incredibly important to how we control microbial growth. So for example, you probably can see a couple of foods up here where, at least two, where acid is actually being used to control microbial growth. Can anybody pick those out?
The food?
Yeah, foods. Do you have?
Like the wine or pickles.
Wine and pickles, perfect. Lactic acid fermentation, which we'll talk about down the road, is a way to control microbial growth. Acid will kill most microorganisms if they're allowed to stay in that condition for a long enough period of time. And that is why the stomach is a great first line of defense against bacterial infection. pH of the stomach, somewhere around 1. It's only like one microorganism that I know of that actually can reside in the stomach for very long periods of time. Most others transiently will go through it, but even that 8-hour period of contact time with the stomach is enough to kill the vast majority of them. We also have bases, which are really good for controlling growth. Any common ones up there that folks notice? Go ahead. Ammonia is a great one. I use it to clean my floors at home. Any others? One that should be in every single household, probably.
Bleach.
Bleach. It's destroyed many clothes of mine. Okay. Another great way to control microbial growth. And really the effect here is, if you're thinking about this at a cell or molecular level, what's happening is it disrupts the proteins. It leads to protein unfolding by disrupting the hydrogen bonds that those proteins typically have in water solutions. This is kind of one of those topics where, like, this is about the only time we're going to cover it in this particular unit, or in macromolecules. We'll come back to it when we talk about metabolism. We'll come back to it again when we talk about growth control. So this is kind of one of those topics, and you'll see this frequently, where we revisit it 2 or 3 times, but in different aspects. All right, let me see. And then the last thing I wanted to make sure we cover are buffered systems. So, Sydney, okay. I was listening to Sydney's explanation. Do you want to offer it up, or?
Sure.
Okay. So what it basically even by analogy, describe to us what a buffer does, or what it is.
Basically like a sponge that picks up like excess hydrogen ions, and then it makes the carbonic acids.
Yeah.
And then when it has like an excess amount of it, then it will like wring out and release hydrogen ions, and then can make water.
Good. You listened to the mini lecture, didn't you? Yeah, that's the example I use, is the idea of like a sponge. So absorb or pick up hydrogen ions or release hydrogen ions when they're needed in solution as a way to minimize change in pH, essentially. These buffers oftentimes have a negative charge on them when at neutral pH, which allows for that absorption of hydrogen ions, or in the case of this one, it actually can release 2 hydrogen ions if the pH becomes too basic. And this, we won't revisit as much, but I did want to bring it up because we oftentimes talk about how the cytoplasm, for example, is a buffered condition. And it's examples like this that help us from going into like an acidic shock every time we breathe in and out. So we've got carbonic acid and bicarbonate in our bloodstream to help buffer pH. Okay. I've covered most everything that I want to. So what we're going to do with the last 12 minutes here is kind of break it into 2 pieces. But first I want to see, are there any questions remaining? Okay. So the first thing that I want us to do is, for about 4 or 5 minutes, I don't want to do that. There we go. I want you to take the following terms. Hydrogen bonding, which I'll just write here as H bond, polarity, polar and nonpolar, covalent bond, hydrophilic, and hydrophobic. Who has done concept mapping before? Few. Okay. So concept mapping, if you think back to like in elementary school where you had to write a paper and they would have you kind of like say, here's the main idea and here are the 3 things that I'm going to use to support my argument. Concept map in some ways looks the same, but the goal of a concept map is to take these terms and show what are the interactions between them. And so for example, I could say something like hydrogen bonds are produced as a result of polarity. I would draw an arrow from polar to hydrogen bond, and I would write a description in between the two. So something like polar, and then I would write bonds create the ability to hydrogen bond, or something like that. And the goal is to just try to connect these different terms together. This is one way that you might find useful down the road as a way to kind of mentally connect some of this terminology and really take it from definition to utility in how you talk about microbiology. So on your own, in pairs, again, doesn't really matter. Take about 4 minutes, and then we'll go over a couple of examples of what you've produced. All right.